Okay, so welcome everybody to this course on TVB-multiscale, which is a toolbox for multiscale co-simulation of the virtual brain with neural network, spiking neural network simulators. I'm going to go through some slides first to describe a little bit the motivation and the implementation of the toolbox, a little bit of science, a little bit of engineering and software structure behind it. And then I hope that there will be at least half an hour in the end to go and run an example on notebook and maybe have some time to play with it also. And at that point, you will check if you manage to get access to register for eBrains and get access to the app that runs TVB-multiscale there. Otherwise, you can just follow and you can play with it at a later moment. So, okay. So first of all, I hope that by now, after I think 6 lectures on TVB, and especially after the first 2 of with Professor Petra Ritter and Michael Schirner, I guess you have now a quite clear picture about the unique advantages of the virtual brain as a simulator that can link brain anatomical data like structural MRI, CT scans, etc., to functional neuroimaging data such as EEG, fMRI, etc., based on its unique property to model and simulate the brain at a level of detail which is the one that is more relevant for the generation of such neuroimaging signals. Neuroscience right now is at the moment that generates tons of this data, and having a generative model that can generate virtual neural source activity and therefore also virtual fMRI, EEG, MEG, etc., in which we can compare with the actual data we get from people or animals. So having such a tool, it's very important to, well, it can help us develop theories. Now there is also a lot of research for developing diagnostics for personalized medicine. I think you went through all this in previous courses. At the same time, there is a very large literature and very many examples of very good spiking neural network simulators like NEST, Anarchy, and Neuron that we're gonna see today in the talk, which are specialized for fine-scale simulation for the investigation of local systems neural mechanisms. So it's a completely different level of modeling that models individual neurons or even compartments of neurons in order to describe and study mechanisms, dynamical mechanisms at this level of description. Now, we think that there are many cases where interfacing the 2 scales and simulating them at the same time and exchanging data from one scale to the other backwards might be beneficial. I will go to later slides to why this could be the case. For the moment, I just want to make sure that we understand a very basic thing. How can we really interface these 2 very distant scales? On the one hand, we have the large scale of brain regions, each one of which might contain millions or billions of neurons. On the other hand, we have neural networks that can have a specific number of neurons, from tens to millions or billions. These 2 scales are very distant one from the other, but luckily, there is the mesoscale, or the so-called populations level scale, that can act as a bridge between them. This is possible because, on the one hand, the state variables of the mean field average dynamical systems TVB uses as models for its brain region. So the state variables of these models generally represent the dynamics of statistical averages of neural populations. So it can be the average membrane potential, the average synaptic activity, or the average firing rate of a population of neurons. At the same time, such averages can be computed also for neural networks of spiking neurons. And therefore, we have this level of the same kind of description. We can convert average activities to individual neurons activities and backwards. At the same time, we have this description in the TVB mean field models, or neural mass as they're called. So that's very important because this population level is going to be the bridge between the two scales. Now, as I said, why would we do that? Let's stay a little bit more on this. Well, on the one hand, it might be useful to create a biologically realistic spatiotemporal context for our spiking neural networks. Generally, when we build a spiking neural network model of a specific system or local network anyway, we kind of driving it either with noise, like Poisson generated spike trains, or with some oscillation, if what we're studying includes oscillatory dynamics, which represent the environment, the rest of the brain, let's say. Now, it can be the case that this is not enough, and we really want to send a differentiated input to such a spiking network that is differentiated either in terms of the oscillatory content, the brain rhythms, in other words, or to have an input that is coming differently from different brain regions, or both, actually. So this is what TVB can do very well for such a spiking network. Assuming, of course, that such an input then also make substantial changes to the function of the spiking network itself. In another case, we might want to have actually bidirectional coupling, so that not only we create this realistic context for the spiking networks, but also this changes the function of the spiking networks and subsequently changes the feedback towards the mean field, the large scale of the brain, and causes then whole brain changes in the operation of the brain. This second case actually is much more important and makes more sense for such a multiscale co-simulation. Let's see some examples in that. So we have already, well, let's start with the fact that the first example interfaces, for the first example, we use the part of TVB-multiscale that interfaces TVB with Anarchy. So first I need to tell you that Anarchy is a spiking neural network simulator that its main benefit, it has many others, but it particularly makes it very easy to include new neural models by easily writing the equations and parameters of each one of them. And then it helps you simulate them. So we have already published a paper using this TVB Anarchy interface and co-simulation in the example of basal ganglia and thalamus neural network connecting to the rest of the brain. So the basal ganglia and thalamus are an STN, are regions that are modeled as spiking networks using Anarchy, whereas the rest of the brain is actually modeled in TVB, and each region is modeled with a mean field model. Now, this kind of network was already optimized in previous studies for control, healthy control, and Parkinsonian patients. So it was shown that different weights of these connections between the spiking populations corresponding to dynamics that were more similar for healthy and for Parkinsonian patients. And then we apply a kind of DBS, deep brain stimulation, to some of these populations in order to bring the patient network back to normal activity, where normal activity here means specific firing rates, mainly of the thalamus, because as you see, thalamus and STN are the main populations that output back to TVB. So we managed to do that. If we focus here on the firing rates of thalamus, we see that the second bar is the patient resting state, which has a lower rate than the control, healthy control. And then the other three are different stimulation examples. So we see the firing rate that approaches back to the healthy normal. Now, this could be done obviously without TVB. However, the fact that this network is connected to TVB allows us also to see how the whole brain TVB activity changes after the DBS stimulation. In another case that we are currently working already now, actually it's in work in progress. In this case, we interface TVB with another spiking simulator, NEST. I have to say that we are mostly working with NEST right now, but you will see also, you already saw an example with Anarchy, and we'll also show you an example with another spiking simulator, Neuron. Sorry? Shall we mute? Yeah, anyway. So in this project, we are modeling the mouse brain dynamics when the mouse is freely performing a whisking behavior. And what we're trying to reproduce is an experimental result that shows that the cerebellum actually is responsible for the dynamics we observe in this behavior. And when cerebellum is deactivated, then coherence in the gamma frequency band between the M1 and S1 cortices drops. In order to do that, we are formulating a network where parts of the cerebellar cortex and cerebral nuclei and inferior olivary complex in the medulla are modeled as an S-spiking network, whereas the rest of the brain is modeled through mean field. It's modeled in TVB. And there are specific connections that you see in this image. I will not go into details, that are more important for this whisking task. What is here also important is that the cortex is modeled through its loops with thalamus. So for every cortical region, there is also a specific thalamus region that formulates this thalamocortical loop. The essence of this model is that the whisking behavior is modeled as a stimulus, a sinusoidal rhythmic stimulus that is given to specific subcortical regions of TVB. And on the one hand, it travels directly to the S1 barrel field, so the sensory cortex. But on the other hand, it goes mainly through the cerebellum, which is modeled as an S-spiking network, and then to the M1 cortex, primary motor area. So the coherence then in the gamma band between these regions is modulated by this activity that is relates to the whisking behavior, which is modeled as an oscillation in the theta band, and on a slower band, in other words, and it goes through the cerebellum. So what we're studying in this work is how important it is to really model in detail the cerebellum, first of all, against modeling it as a mean field without so much specific connectivity and dynamics, and also whether we can reproduce in both cases the drop in the gamma coherence in the cortex when the cerebellum doesn't function properly. So I want to emphasize the fact that here there is really a loop between the two scales. As the stimulus comes from the large scale of TVB, it goes through the fine scale of the spiking networks and the specific dynamics and mechanism modeled there in order to substantially change the behavior on the large scale as the coherence between M1 and S1. So this is really a very good example about why such multi-scale co-simulation might be useful. So let's see now a little bit how we can actually do this, how we can couple between the two scales. So I mentioned two kinds of scenario. One is where we model only in one direction, we interface in one direction. So mean field nodes of the brain, so regions modeled with mean field, average models, couple and create a context to spiking network regions. And this could be a case, for instance, that we don't really substitute a region with a spiking network, assuming that the spiking network is a very small network that doesn't really affect the large scale, and we're only interested in the context the brain creates for this small network. Alternatively, most of the examples I'm going to show you is about bidirectional connectivity, in which case we actually can substitute a whole brain region with spiking populations. And in that case, we need, on the one hand, to couple from all other mean field regions to the spiking region. And at the same time, we don't want to create a hole in the TVB brain, an empty space for that node. We actually need to record the activity of the spiking region and somehow update, create a mean field representation of this activity and inform TVB so that this node can keep existing and producing EEG, fMRI, and everything else for the whole TVB brain. So that's important because on the one side, we have a coupling, some region modeled in TVB. I will always use the indice N prime for those regions, couples to a spiking region node. I will use the N index for that. Whereas on the other direction, a spiking region N, a spiking region N actually updates the corresponding, the same node N as a mean field in the TVB network so that we have the integrity of the TVB network. So let's see how we can work out these couplings and updates. So starting from the TVB to nest coupling, what we need is actually to get a state variable as it dynamically changes in time. And at every time moment, we need to somehow convert this mean field activity to individual spiking activity through some kind of transformation, and then find a way to inject this activity in the spiking network. So for every node and prime of TVB, we need to have a representation of that node inside the spiking node, what we call a TVB proxy, that mimics the activity of the mean field, only now generated as individual neurons activity, and stimulate with that the spiking regions N that are modeled as spiking populations. For instance, here in this example, we have an excitatory and an inhibitory population. Such connections need to respect the TVB connectivity that has, as you have seen in previous courses, a specific weight, scaling the strength of the connections, and a specific time delay between every node N prime and every node N. Of course, there is also a variation of this because we already know that TVB computes the coupling for every node. So in principle, instead of creating one proxy node for every TVB node that sends data to nest, we could actually compute first the coupling that should be directed towards this spiking region, and then make the conversion and create only one proxy node for every receiving region in nest. This is a much more economic way, of course, because we need much less proxies, TVB proxies. But on the other hand, it might not allow us, for instance, to build, let's say, for instance, different synaptic plasticity dynamics for different regions. So in this case, first coupling is computed in TVB, like for any other node. And then this coupling activity is converted into spiking activity, and then a nest simulating device or TVB proxy is sending this activity to the target spiking regions. Only this time, there is no weight or delay. Weight is 1, delay is the minimum delay of the resolution of the spiking network, the spiking simulator. Because this has been already taken into consideration during the coupling computation in TVB, both the weights of TVB and the delays. Now, in the other direction, we said it's an update, not a coupling. What we need to do actually is record the spikes emitted or any other kind of activity, but we currently work with spikes only, of the spiking populations of the spiking regions. And as we count the spikes, we can compute instantaneous firing rates and therefore transform the spiking activity into mean field activity, and then go and overwrite the respective activity of the state variables of the TVB mean field model. So several conversions again might be needed here, But the idea is that specifically for the regions that are modeled in NEST, it's not the same equations working as if for other nodes of TVB, because the activity is actually coming from NEST and it's overriding the activity that would be normally computed in TVB. But this happens only for the nodes that are modeled in NEST. Let's see now a specific implementation, just to see a little bit of a few of the details, the difficulties one might find. We start with the integrated fire spiking neuron model. It's a model well known in the literature called Wang, and the reason that it's one reason that is well known is that there has been a reduction of this model to a mean field model. So a model, in other words, a neural mass model that models the dynamics of a population of actually two populations, an excitatory and inhibitory one, of neurons of this kind. I will go very briefly through the equations. So the spiking model has dynamics for the membrane potential of the neuron of this kind. There are several currents that feed into the equation of the membrane potential. Each current has its own synaptic gating dynamics. And the currents are excitatory local currents like AMPA and NMDA synapses, and inhibitory ones, GABA synapses. There can be also long-range excitatory connections, for instance, with an AMPA synapse. And each synapse has its own dynamics. It's linear for AMPA and GABA, and linear at one dimension, actually, and it's non-linear and two-dimensional for the NMDA synapse. And these synapses are activated by incoming spikes from other neurons. This happens locally within its population and also for long-range connections. Now, the reduced mean field model, the state variables of this model that you can find in TVB, has a state variable for the excitatory population and then a state variable for the inhibitory population. These state variables describe the synaptic gating dynamics. Variables that are scaled between 0 and 1 are constrained between 0 and 1 because they represent the percentage of channels, synaptic channels that are open at any time. The equations following that these state variables follow, you can see them here. It's a linear one for the inhibitory and a non-linear one for the excitatory. And the only important input here is actually the postsynaptic rates of its population. Those rates are given by a sigmoidal activation function, like the one you see here, the input being the presynaptic currents. Now, those currents are similar to those currents here. There are some constant output inputs that represent the rest of the brain, let's say. There is a local excitatory NMDA current, inhibitory GABA currents, and long-range NMDA currents for the excitatory population. It's similar for the inhibitory population. Now, to get a current from a synaptic gating variable, one needs to multiply with this constant in this case. So there is a correspondence, a supposed, actually an actual correspondence between these two models, and assumingly a network of the whole brain that uses this model or a network of the whole brain that uses populations of spiking neurons of this kind should in principle show similar behavior, not absolutely the same, but similar. So now the question comes, how can we take a couple of regions, for instance, and remove the mean field model and actually place their populations of neurons? How would they, in this case, the two scales communicate? So as we said, one way is to take instantaneous rates of the mean field models, convert them into spike trains, for instance, through some Poisson spike or other kind of spike generator. And then, of course, this would inform the corresponding synaptic gate variable according to these equations. Another way is, since this model already has a representation of currents, we could actually send currents to this model directly for this external connectivity between different regions. And then how would we update them? As we said, specifically for the models N, or the regions N, that are modeled as spiking regions, these equations wouldn't really function, and instead, the rate could be overwritten by updates from the spikes that the actual neurons generate in these spiking regions, and then the rest of the equations could function. Now, getting into more technical details about how we can do this. So first, when we transfer rates, one way is to take the rate of every TVB node and instantaneously, for every time point, update a proxy node of TVB inside Nest network, modeled, for instance, in this case, as a Nest device generating spikes. And therefore, these spikes would be generated and sent to the target spiking region nodes, to its population. And that would happen with weights from the TVB connectivity as well as time delays between regions according to the TVB connectivity. Another way, as we said, would be to instead send currents. So we send actually the synaptic gating variable in the transformer. We actually multiply to make it a current. And then we actually use a Nest device generating DC currents instead of spikes. And similarly with weights and time delays based on TVB connectivity. But alternatively, we could actually first compute the coupling of total synaptic activity towards its spiking region N, and then it could be the coupling transfer to Nest, in which case we would need much less TVB proxies, one for every receiving node in Nest instead of one for every sending node, and which is actually faster. And finally, for the Nest to TVB update, as we said, we can count the spikes using a spike detector device that is available in Nest. So counting the spikes for every population and then converting it to a mean firing activity for every time step. And then this activity would go and overwrite these rate variables in TVB, deleting, let's say in some sense, the equations that compute rates from currents in TVB for the specific nodes that are modeled in Nest. Now all this sounds as easy, but it's not. There are many details there, and I'm going to show you one example, for instance. Let's start with a network with only two regions modeled in TVB on the left, or the same network of only two regions modeled as in Nest, and respecting all the parameters like number of neurons, etc., that were used in the paper that derived the mean field model from the Nest spiking, from the spiking neural network model. The paper, in other words, that derived the mean field representation, the average representation of the dynamics of the spiking network. And what I'm doing here is I'm creating a bifurcation diagram for each of the two networks of the average firing rate activity of the excitatory population, depending on two parameters: the self-excitation of the excitatory coupling, this W plus, and the coupling strength between the two nodes, the two regions. And what we see in both cases is that actually this model can show bistability in the sense that there is a low activity equilibrium point as well as a high activity equilibrium point. And for some regions of these two parameters, both states can be stable, so both states can appear. And different values of the W parameter here are represented as different colors, whereas you can see the G values on the x-axis and the firing rate equilibrium on the y-axis. And you can see where the bistability ends and only the high activity is stable from that point on, following this dotted line. But what you see here is two things. First of all, that for the same pairs of sets of parameters, the bifurcation points are different. For instance, if we take a color of it, let's say the green one, for instance, here the bifurcation happens at value 50. Okay, I didn't. And here the green one that happens at value 50 is actually corresponds to a different W plus parameter. So there is a difference, a quantitative difference between the parameter values. At the same time, the shape of the bifurcation diagram is different. That means that if we had the brain and we had several mean-field nodes and then some spiking nodes, and we created a multi-scale co-simulation model, the large scale, the average activity of the spiking regions would be qualitatively and quantitatively different than the one of the mean field, and therefore the whole brain dynamics would change when substituting a mean field node with a spiking node. Is there a way to correct for this? Well, what I did in this case was to select, first of all, a pair of values where the bifurcation point is similar. So one, for instance, where W plus is 1.3 for the spiking network and 0.9 for the mean field nodes. And then the second thing I did was to make a nonlinear transformation of spike rate to firing rate, mean field firing rate, and the other way around. So in other words, when I couple the mean field rate of TVB nodes to create spike trains for the spiking network, this conversion is nonlinear, this mapping, let's say. And similarly, when I update TVB nodes with the nest activity of the spiking activity, I also make a nonlinear conversion. If I do that, and then I can couple, I can create a network with one mean field node and one spiking node, then the average, the large scale activity of both nodes follows the bifurcation diagram of the mean field node. This would mean that then if I follow this, and I could substitute mean field nodes with spiking nodes, and I would get both the specific spiking dynamics locally for every spiking region, and at the same time, I would get the desired large-scale activity. The spiking regions wouldn't be qualitatively or quantitatively different, or at least to some degree. They wouldn't be different with the mean field nodes, and therefore the large-scale whole brain dynamics could be similar. So that's just an example to show you the complications. Obviously, converting average activity to individual activity and backwards is a whole chapter and an open field of research. I just wanted to that you get a picture of it. Now, I'm going to show you another example. This time, some colleagues of us have implemented a TVB Netbind interface. Netbind is actually a Python interface to the Neuron simulator. So why is this important? Because actually Neuron is a simulator that is the one that is mostly used in the literature. Most models and papers actually use Neuron. So it's very important if we can couple TVB to Neuron as well, and because also Neuron allows for multi-compartmental neuronal models. And Netbind is actually, as I said, an interface that makes it much easier to develop and simulate models with neuron spiking networks. Here there is an example where neuron code, it becomes much simpler in Netbind code, whereas there is also a GUI for Netbind. So you can find all details about Netbind following these links and reading the paper of our colleagues. What I'm going to quickly show you is that actually our colleague Valerie has implemented the same network, more or less, of a whole brain using reduced one mean field models, and only 2 regions are modeled as spiking neurons. But instead of the neuronal model you saw earlier, he uses a model that is much more detailed. It is a biophysically detailed model. However, the interface is similar. It is based on a rate conversion to spikes. I won't go into detail because it's actually the same principle. And the other way, Netbind to TVB update is implemented in a similar way. And we get the resulting simulations. Here you see the rate of the excitatory population for all TVB nodes. And you can see that for the 2 that were modeled as spiking regions, we see a kind of different behavior that looks more like oscillatory coordinated spiking activity. And if we zoom, we see this kind of activity here. But this is to show you that how the spiking network updates TVB, and therefore TVB time series contain the activity of the spiking network, whereas all other regions are actually simulated according to TVB equations. And then we can also look at the activity through Netbind. Here we see the different neuronal populations and the same kind of activity we saw before. So, in other words, TVB Netbind is there and people can already start using it. So, I will spend a little bit more time before the break to get into some more details about the software itself, which you can find following this link in GitHub. It's public. And here I'm not giving you the link of the master branch because it's outdated. Generally, the tool is under heavy development, so documentation and testing are not developed enough. And yeah, so I'm giving you a link of the branch that is more up to date and the one that I would suggest that you use if you want to play with it. So yeah, I'm going to talk a little bit about the toolbox. It has several components that are modeled as distinct software classes. First of all, there is a TVB model and simulator taken from TVB. Then I have generated wrappers around objects of the spiking simulators, scaling from neurons to populations and whole brain regions. I'm using Panda series for that so that I can address regions and populations within regions, both by index and by name. And then there are also representations of the TVB proxy nodes inside the spiking network as spiking devices or populations, stimulating the spiking network or measuring its activity. And then there are other classes that are responsible for sending data between the two simulators or for transforming the activities from mean field to spike activity and backwards. And then there are other classes that actually make combinations of communicators, transformers, and models in order to, in the end, bring them all together. Now, all these different components are coded and are linked in a modular way, such that people can change one or the other and then link them to the rest. And so that in the future, not yet, unfortunately, we can have multiprocessing and several of these components working on remote resources. This would allow a better performance and scalability of the whole co-simulation. So we have, as I said, TVB models, spiking models, proxy models, transformers, and all the other classes that help us send data from one to the other. Now, as I said, interfaces, what I call an interface class, is a class that is composite of different of these components. For instance, the most complicated example would be interfaces where the TVB model, the spiking model, the transformers are all working on 4 different remote processes in parallel. In this case, for instance, a TVB interface would only send and receive data. Similarly, a nest interface would contain the TVB proxies and the senders and receivers, where a transformer interface would contain the transformer itself and also the receiver and sender of data. In other cases, it would make more sense actually to have the nest network, which is mostly the bottleneck in co-simulation if you have millions or billions of neurons working on a separate process, and having then only a nest input and a nest output interface, whereas everything else would be a TVB transformer interface combining TVB and transformers in the same process. That's another example. This is what I mean by modularity. We can build interfaces by combining components here. Another important issue is the synchronization between the 2 simulators, because they both simulate in time and they need to exchange data at particular moments so that co-simulation continues. So one way is to actually model one step, to simulate one step of TVB, send data to nest, for instance, then simulate one step of nest, send data to TVB, etc. In other words, synchronize every time step and simulate serially. In that case, when we send TVB data to Nest, we send, let's say, rate data, for instance, at time t, and these are converted to spikes that are going to be probably applied with some time delay. And when we update activity at a specific spiking activity of a specific time moment t, and this will be converted to a rate of the same time moment. Another option is to take advantage of the fact that brain regions are actually connected always through some time delay. And therefore, every region doesn't need data from other regions unless this time delay has arrived. And therefore, we can model, we can link, we can synchronize TVB with Nest every minimum delay time. So we still simulate serially, but this time we don't synchronize at every time step, but only at every minimum time delay. In this case, data from an interval spanning the minimum delay time would be converted similarly to spiking activity and probably also applied with a time delay. Finally, ideally, we would like to both synchronize every minimum time delay, because every synchronization takes time, obviously, and at the same time, exploit the time between synchronization to simulate in parallel. This is the final objective. And why is it the final objective out of these three ways? Well, because it has been shown already by our colleague Lionel Couche of INS in Marseille that it is actually the way performing better as the number of neurons in the spiking neural network increase. So here in blue, we have single-step synchronization and serial co-simulation. In orange, we have delayed synchronization, but still serial co-simulation. And finally, in green, we have both parallelism and delayed synchronization. And you can see that the computation time is much less than in the other two cases. Moreover, as I said, we have different classes for all these components: transformers, communicators, senders, receivers, models, etc. Additionally, there are classes which we call builders. These classes are responsible, for instance, a TVB mod, a simulator builder can build a TVB simulator, a spiking network builder can create a spiking network, a communicator builder can build a communicator. This allows the user to configure a builder and through that configure actually a model. So these builders, after they're configured, they also represent a model and also create the models in a way that is consistent. There are several checks we're doing there, etc. So at the same time, the builders represent the models and at the same time help the non-expert user to create their first models. So some of these builders are opinionated, so they present specific models we have already implemented. And other builders are non-opinionated, so you need to put your own input there in order to create the models. At the same time, there are TVB apps, SpikeNet apps, and orchestrator or simulation manager apps that help you set up the models and run the co-simulation. I'm not going to show you in the example all this because in the notebook, I will show you an example where the user puts himself much more input by hand so that you see the most important parts of this process. But you're welcome to test everything by running the code yourself. The default workflow, what we usually do in order to generate co-simulation is, first of all, we need to configure a configuration that decides for the main parameters of co-simulation. Most importantly, about the integration resolution, how often, the time step of the simulation, as well as the synchronization time between TVB and Nest. Then we first build the TVB model and simulator in the usual way you might have already seen in previous courses, and I'm going to show you soon. And then we build the spiking network model. Then we create the interfaces between them. And finally, we simulate, and then there are also some tools to gather the results, write them to files, analyze, plot, or you can, of course, use your own code for that. I'm showing you here an example if one uses an orchestrator, for instance, and as this orchestrator is quite opinionated also, the user can actually set only very few inputs, like create here the TVB model, create the nest model, configure the interfaces, and then run. This can be done, in other words, in only a few lines. But again, as I said, it's better we go through an example with more details. And the most important part, which I just want to mention here, is that it is generally very easy to set up the interfaces, which is the core of the software. Usually everything is set as a list of dictionaries of configurations. The main thing is to create the mappings between the state variables of TVB and the population names of the spiking neurons. And then there are easy ways to choose the kind of interface, a rate or a current, etc., and set some parameters for the different transformations. You're going to see soon an example of that. So you can find the code, you can run the app, as we're going to try to do in a while. And you can find more information about all this in the corresponding collaboratory of eBrains. I want to mention that there is a lot of work still to be done. As I said, the toolbox is under heavy development still. And at the same time, there is a lot of science that needs to be done. We need to test such multi-scale co-simulation in different use cases and compare the different interfaces, validate them the way you saw, for instance, with this parameter set exploration I showed you before. There are technicalities. We need to optimize co-simulation to increase speed and parallelization and optimal use of eBrains hardware resources. There is a lot of work to be done to improve documentation, test coverage, and generally the usability of TVB in clusters. And well, the most interesting part is, of course, to use the toolbox in real science problems. So there are several references you can look. And at this point, I think we could have a break maybe and be back in, let's say, 5:35, for instance, in 13 minutes. And then we could go through an example. And actually, already I can close this and maybe show you a little bit so that you can be ready for it. So, unfortunately, for some reason, my computer is very slow right now. So I have already shared with you the collaboratory that I prepared for this course. You can find the slides here and some instructions on how to run the example. And I hope you have all created accounts in eBrains, because then you can log in. This collaborative is public. You can look at the resources without registering, but you will not be able to run the app. So how can we run the app? I will show you that now so that maybe you can prepare it for after the break. So here is the path to the app. All you need is to run it. And you're gonna end up on a page like this, and it will ask you to sign in. And if you're a TVB eBrains user, sorry, an eBrains user, registered user, you're gonna get into a screen like this. And as I have already created this for me several times, it runs fast. But for you, it might take a lot of time. You might need to refresh a few times. And if many of you go to do it at the same time, there might be problems. So I suggest that you better start already. And then if you manage to do that, all you need to do is get into this folder, document it, and you can actually copy this notebook. You can say here, duplicate and then move, and put it better inside the folder, inside this folder, because then whatever changes you do will be saved for your own account, because this folder offers persistent storage. Otherwise, if you only run it through this folder, as I'm going to do right now, after you log out, everything will be lost, every change you have done. So this is the notebook we're going to run in 10 minutes from now, and you can try to also run it. So let's be back in 5:35 for your time. So I hope you're all back so that we can go through the hands-on session, and particularly through an example of running a notebook for TVB multiscale course simulation. So I will not go through these introductory slides since we just discussed about this. I will only say that unlike the model I showed you earlier with the reduced Wang neuron, here we are going to use a different mean field model, Wilson-Cowan, which also can be found in TVB, and it also contains an excitatory and inhibitory population, and it's also very widely used in the literature and in TVB simulations. And also an integrated fire neuron from neuronal model in NEST, the equations of which you can see here. It's quite similar to what we saw before. Actually, it's simpler because it only contains an excitatory and an inhibitory synapse here. I'm not going to go into the details of the equation, doesn't make a difference here. I will only continue with the actual code. So as we discussed, the default workflow for running such a simulation is to first determine several wait a moment, this is not the model I expected. Okay, wait a moment, there has been a mistake, and the mistake actually was that I'm running the wrong app. Because this is actually so. This means I have given not the correct link. So let me help you also correct my mistake. So you need to correct here the address so that it is TVB-nest minus dev, the development version. I'm sorry about this, the link was wrong. We're going to end up again to this login in page. So I'll wait a couple of minutes in case you have difficulties now to recreate this. Because again, it's going to be the first time you do it. I'm sorry about this. I should have, well, while you try to do it, I will correct here the link. And we also have a look of how we work with collaboratories. Right, this is the error. All right, well, I hope that now you have managed to connect to the correct app. Again, we have this folder of the documented example notebooks, and we're going to run this notebook here. You're actually now in a page of Jupyter Lab, not just Jupyter Notebook. And as I said already, if you copy this into the, everything is very slow, I'm sorry about this. I don't know if it is my computer, because I think the GoToMeeting makes it slow, or if it is because...
Denis,
yeah?
Can you
Yes?
please post the link in the chat?
Yes, of course, of course.
Thank you.
Okay, I will go a little bit again through all this copying and pasting, which you can also do after the example, of course, so don't worry. Just to give you a little bit more time for those of you who are trying to follow. So generally, when you first, it's so slow, I'm sorry about that. Yeah, so when you first connect, you're going to be at this point here. And as I said, whatever you add to this contributed notebooks folder, it's going to have persistent storage, and you can come to it later on after you log out. Otherwise, whatever we do now here, it's going to be deleted after we log out. Right, so we are back to the notebook. This is another version running a more updated version of the TVB-multiscale. And here we also see the equations of the Wilson-Cowan TVB mean-field model. And as I said, we first start with several configurations. I hope also the screen is big enough. And I wonder if I can remove this. Okay. Right. Now, there is already a configuration class that is instantiated here. But for an easier read, I have created also some other configurations here so that we can easily change, modify, and run different kinds of simulations. So first of all, this notebook can simulate both a TVB-only model, a nest-only model, or an interface, depending on this input here. So we're going to only run co-simulations, so we don't change this. The second flag determines whether we're going to build the nest network based on predefined opinionated builders, or by configuring ourselves in this notebook a non-opinionated builder, or finally by writing nest code ourselves. So we're going to go very fast through this step because it's not the main. I mean, for a nest expert user, you don't really need to know a lot about this. Otherwise, you might go first through using opinionated builders. There are some basic configurations here, like we have already TVB connectivity, but we might want, and we're going to do so actually, we're going to run a similar example with less regions. So I'm already modifying the notebook. We're going to use a brain of only 4 regions for simulations to run faster. And here we're determining the indices of the nodes we want to model in nest. So let's model the first 2 nodes in nest, and the second and the third and fourth node in TVB. And then we also decide for the number of neurons its population would have. 100 is a good number to observe all the phenomena we want. And here there are some interface basic configurations. We're gonna try, if we have time, to run an example with a rate configuration, in which case TVB sends rates, as we said, to nest, and spikes are generated over there, or a spikes configuration interface, sorry, in which case spikes are generated outside nest on the transformer level using the Elephant software. And then these spikes are actually transferred to the nest network, or a current interface, in which case it is current values that are sent from TVB to nest, and then current stimulating devices, the so-called DC generators, are used to couple with the nest region inside the nest network. And then here is another important input, because as we said, one way is to compute coupling in TVB, and then send the coupling towards spiking regions to nest, in which case we need less TVB proxies. We need 1 TVB proxy device for every receiving nest network and nest region. Or conversely, if we set the flag to SpikeNet, we create one TVB proxy for every sending region of TVB. This means we create many more, well, not in this case that we have only 4 regions, but in the general case of many TVB regions, this would require more proxy nodes and would be generally slower. And finally, this is a very basic scaling of the coupling from TVB to nest. So increasing this value would make stronger the coupling from the TVB regions to the nest regions. Reducing it or making it 0 would actually reduce this coupling. And I have tuned this coupling already for the main example of rate and TVB coupling. And then, as you're going to see below, I have adjusted it for the different other models so that the result of the resulting firing rates for the nest neuron populations are pretty much stable. But it's something you can play with also. The rest of the configurations are not important. And so we can actually try to run until here, the notebook, which is extremely slow. And hope that nothing strange will happen. So then we first need to configure the TVB model. I don't know if you have, so there are several messages here. We ignore them for the moment. I hope you have seen some example of configuring a TVB simulation through a script before, but for the moment I can tell you that the main steps of that is that one needs to configure a connectivity. Connectivity usually by loading some data of connection weights and connection distances that are converted to time delays. And also one needs to define the kind of mean field model we want to place at each brain region, the coupling function, which in this case is just a linear scaling of the activity of one node affecting the other nodes. And we also need to select how to integrate the model, the particular algorithm, the time step of integration, and whether we're going to have some noise added and its amplitude. And it's also good practice to define the initial conditions of the system. Finally, we need to record this activity somehow. And here I'm only defining a raw monitor. We will just return the source activity of TVB with the time resolution defined here as 1 millisecond. So when I say source activity, actually we're going to get for every brain region the activity of the excitatory and the inhibitory population. So these 2 state variables. Now, we can also define the model parameters. I have put parameters in such a way that we get oscillations around 20 Hertz, if I'm not mistaken. We're going to see that. And here I'm also reducing the connectivity because, as we said, we're going to make an example of less brain regions so that simulation runs faster. There are several normalizations we can do to the connectivity so that the range of values is not too large. And all of these configurations here, we are doing them explicitly. Alternatively, we could comment this part of the code and instead use the simulation builder class, which it's included in the TVB-multiscale toolbox, and this builder can be configured with basic choices. And then the builder goes through steps and checks also for consistency and eventually returns the simulator for TVB. So we can run this cell and hopefully we're going to get the TVB simulator configured and the plot of the connectivity. Also, we serialize the simulator to a dictionary and we save it to a file. This would be used if the nest simulator runs on a remote process and Then this process would read this file and configure the nest network based on some of the parameters of the TVB model. Here we're just printing this dictionary of properties of the TVB simulator. You can see all the parameters of the model, for instance. And then there is a plot of the connectivity. I'm not sure how I can... does anyone know how I can have a view of this? Well, I guess no one knows. I'm trying to press here, but...
What do you want? To see the full picture?
Yeah, I would like to see the whole
Normally,
picture.
just double click on the left,
Here?
on this, yeah. Not on the blue line, just inside here.
I think,
wait.
Let me see. No, wait. Oh, now I really reduced it to nothing.
No, you can, in the white part, on the...
Yeah, this is what I thought, but on the white part, right?
This white part, just double click.
Well, I just did, but
it doesn't want.
Yup, anyway. I hope that this means that many of you have connected and that we're sharing limited resources, and that's why everything is slow. But anyway, yeah, nothing happens. So anyway, there is a plot here of the TVB connectivity strengths. So we can see 4 regions connected to 4 regions. It's a square matrix. The first 2 are modeled in nest, the other 2 in TVB. And then there is another plot of the lengths of the connections which determine the time delays. Anyway, on the next step, we now need to build the spiking network. As I said, there are 3 levels of ways to do that. So one way is to actually use opinionated builders that I have already created as examples. And so this would be very little code like this. It would be instantiating the builder with basic inputs. And so these basic inputs correspond to the serialized TVB simulator, the indices of the nodes we model in nest, and the nest instance that has already been loaded and configured. And then we can change a few parameters of this builder, like parameters of the model, for instance. And then we would actually build the model. Alternatively, we can instantiate a non-opinionated builder, in which case we would put more inputs of ourselves. We would create populations of spiking neurons. We would give a label. We would choose the model of the neuron. We would set parameters of the neuron if we want to put some of them. And we would decide how many neurons. So the scale is a float that is multiplied by the basic number of neurons that we have defined as 100 at the beginning. And yeah, we define it here so that each population can have different number of neurons. And then we decide if this kind of population will be created for all brain regions, which is the case we've set none here, or into only some of the brain regions. Then we need to define connections within each population. Again, it's the same kind of input, a list of dictionaries, each one creating a kind of connection. We can address populations by the label. So for instance, this is the self-excitatory connection from the excitatory population to itself. And we can define the synapse model and inputs that are relevant to nest, like the specification of connectivity. Here it is a node-to-all connectivity, for instance. The weight and the delay of this connection, and the receptor type in case that there are different synapses. These are all nest-related inputs. And again, we need to say if we want this connection to be created in all brain nodes or in some of them only. Similarly, for other connections of the model, then we need to connect populations that exist in different brain regions. because if you remember, we made 2 brain regions model in NEST. So we need to connect those populations also from different brain regions. And in this case, besides the same inputs as before, we need to determine how the weight and delay will be determined based on the TVB connector. And we can do that by defining functions that take into consideration the indices of the source region node and the target region node, and then also the connectivity weights of TVB, and similarly for the delays. In general, most of these inputs, I cannot get into details now, can be determined as functions of the indices of the nodes in case we want to have something like more heterogeneous parameter setting between nodes. And finally, we can also determine some devices that will measure the activity of NEST, like spike recorders, and we give a label to the measurement, and we identify the population we want to record, and the parameters of the spike recorders, the nodes we want to record. And we can also record continuous variables of these spiking models through a multimeter device. Again, we give a label to the measurement, and we record specific populations. So I get a question about spawn failed. It is the kind of error we expect. Yeah, if it doesn't work after a few times, I don't know what to say. It should work in general, but to be honest, I don't know how many resources are available, so I don't know how many of you have tried to connect. This could be a problem. Keep trying just in case it works, and you can also try another time, and you can contact us until we solve the problem. If not today, then in the following days. Yes, but at the same time, try to follow what we're doing, because anyway. So, and also we can define additional stimulation device if we want in a similar manner. So all this actually works like wrapping around NEST commands. The good thing is that most of this would be similar if we were creating an anarchy model or a Netbind model. So this is like code that is TVB-multiscale specific and wraps around the corresponding commands of NEST, Netbind, or anarchy. So for the non-expert user, it makes it easier to build such a spiking network. The builder then would be configured, no matter if it's opinionated or not, and then a NEST network class would be built alike. Now, we can also build this model without using a builder and just using NEST commands directly. And in this case, NEST commands like this are used. But still, we need to create this NEST network class that is TVB-multiscale specific. It contains all the brain regions as different classes, and each brain class contains all the region nodes, and each region node contains NEST populations. This is, as I said, based on pandas series. So for instance, NEST network brain region inherits a panda series so that we can address every region both by index 0, 1, 2, 3 and by name. And the same is true for every brain region. It's also a panda series, and we can address every population by index or by label. So this loop, for instance, would create the same populations and on the same brain regions like before, and directly place them inside these classes, but using directly NEST commands. So for users that are more accustomed and can run their own NEST commands, maybe this is the simplest and better way. And the same goes for creating the desired connections between populations, within regions, and then also between brain regions. So here directly NEST code is used. You can see the similarity of the inputs. And the same is true also for the devices. The devices are also created inside the Panda series, and then each device records or stimulates a specific population for several brain regions. So that means that there is a Panda series, for instance, of output devices that can be addressed by the measurement name or the population name. And each one of these is again a Panda series. And for every region, we can again address by index or by name. So this is actually the opposite scheme, like brain regions. Brain regions are first indexed by region name and then by population, while here, first we index devices based on what they measure, and then by region if this device exists in different regions. Similarly, for input devices, for instance, we give a name for this device set, as it's called. It's an input stimulus, generating spikes in this case, and we address it by region then. So in both cases, there is a nest network class created. I think the way we're going to create it now is by using this kind of directly nest code. Several messages are printed upon creating this network. And in the end, there is also a summary of the created network with informative, I hope, printouts. We can see all the brain regions one by one and their populations and their parameters. So this is a quite detailed printout. If we had the whole brain, it would take a lot of time to print it. Otherwise, we can choose less levels of detail and also to exclude the connectivity information. Otherwise, it will run forever. Trying to print everything, I mean. So now we have built the TVB network and we have built the nest network. And now we are at the point that we need to build the interface between the two. And I hope I could scroll down here. Okay, good. So similarly to building the nest network, we can have an opinionated builder for building an interface where we can store our models as configurations of these builders, or we go through a non-opinionated builder in which we're going to configure in more detail. And first thing we need to do is to give some basic inputs, the configuration, the TVB simulator or the serialized version of it, and the nest network. And we need to define the kind of coupling we want from TVB to nest. And we define here, we define this on the first cell to be rate for the moment. We determine whether we want TVB to receive input from nest and send output to nest. So by putting these flags to true, we'll do both bidirectional. We determine whether we want coupling to be computed in TVB, as we have chosen right now, or this more detailed version where we generate one proxy for every TVB node, in which case coupling with weights and delays is taken care of by nest. Yeah, we give some more inputs here, number of neurons of the populations. This is going to be needed for the different scalings. And the indices of the regions modeled in nest. And we're telling the builder that the spiking regions are actually modeled exclusively in TVB, and therefore they are substituting the TVB nodes, and therefore we should remove all connections among those nodes, particularly inside TVB. We initialize then the inputs of the builder for the output and the input interfaces. So again, output interfaces are from TVB to nest, inputs are from nest to TVB. So the sender here is TVB. And then there are several printouts that inform us about the different kinds of models that are available, models of transformers and of interfaces. Okay, I forgot to run the first cell. So you can use those to direct yourself and test different models, different transformers. I cannot go into details because the important detail is really this cell here. It is the cell where we're configuring the builder to actually create the interface models. So what we're going to create here is we're going to take the activity of the excitatory population of every TVB mean-field node. So the state variable here is given by the label E, and we create a mapping with the corresponding excitatory population of the spiking region. So we create the connections from excitatory state variable to excitatory population. We are choosing the model to be a rate model, as we said. We are setting the proxy indices, which in this case, when coupling is computed in TVB, actually correspond to the nest indices. So this input is actually the same as the spiking proxy indices. So these are the indices of the nodes modeling nest. And we decide of the kind of device that will be stimulating nest, in which case it is a device called nesting homogeneous Poisson generator. So it converts rates with a time resolution to spike trains. And we need to decide the model of the transformer, in which case, by choosing rate here, by default, we get just a linear transformer that will just scale the TVB rates into actually the TVB state variable values of this model into rate values. I will go through this scaling in more detail. So these are very basic inputs. Some of them, even if you omit them, they will be filled in by default once you choose the correct model here. The most important thing is choosing the mapping between state variables and populations and the indices. So this is really the three inputs I think that you cannot omit. And then it's very important always to fill in some parameters of the transformers. So in our case, we are sending activities of Wilson-Cowan state variables, and they need to be converted to spiking rates for the neurons. For that, we already defined the scaling. This scaling takes into consideration several things, like the Wilson-Cowan state variables are usually between 0 and 0.5. This needs to be converted to hertz. And then simulation takes place in milliseconds. So we also need to account for this conversion from seconds to milliseconds. So a rate of 2 hertz becomes 2000 when we consider a time of milliseconds. And then also we need to scale with the number of neurons, because TVB mean field activity needs to be converted to total activity of a specific number of neurons. And then there is also an arbitrary scaling, because we want to tune this connection to be stronger or weaker. And so this is the part of the output interfaces from TVB to nest coupling. And then we also want to update TVB with the spiking network activities. So this is the part of update from spiking network to TVB. Again, we need to create mappings between populations and state variables. Here, the labels are exactly the same, and therefore they look the same here. Again, we need to define the nodes that are modeled in nest. And here we choose a model that will take spikes, totals, all the spikes, will count the spikes of all neurons of each population, and then we'll average them with the number of neurons to create an average spike rate. And there are further transformations that need to be done, again, to take into consideration the conversions from milliseconds to seconds, etc. So this is taken care here by the scaling factor of the transformer that is dividing by the number of neurons, and also converting from the type step of integration 0.1 milliseconds to seconds. So these are very basic inputs. I think in just a few lines, you can configure this. Of course, assuming a specific transformer, which is here just a linear scaling mainly. This transformer that converts spikes to rates makes use again of the Elephant software to create a histogram or counting the spikes for every time interval, every time step. Again, we can configure this builder once we have defined all inputs. And there are printouts of the inputs we gave. We can confirm they are correct. And then we can build the interface and attach it to the simulator of TVB. There are messages print out and eventually a printout like before that describes the interfaces that have been generated. What I want to show you is that we have created only one interface because it is the same for both nodes of TVB that send activity coupled to nest nodes. So it's the same interface, and we can see here the indices that are implied, the brain region indices. But in principle, we could have defined many configurations of different kinds of interfaces for different nodes or different populations, and then they would appear here as more interfaces. Again, the structure is a panda series that can be addressed by label or by index. Actually, this anyway. And similarly, for the nest to TVB update, we have created two interfaces because we want to have activity both of the excitatory and the inhibitory population. And you can see these two interfaces here again, and the brain regions involved. Well, that was pretty much the most important step. And then we can just prepare the simulator and run it. The simulation takes time, is very fast in this case because we only have 4 regions. And it's completed. And then I won't go through the details. There are several tools here to plot activity, record it into files. Everything makes use of TVB and TVB-multiscale tools. And also we use the PySpike and Elephant softwares to compute different metrics on the spike dynamics that we have recorded from the nest network. So that eventually we can get plots of the activity of the nest network as well, both of the spiking activity, I'm going to show you in a while, as well as of variables like the membrane potential, for instance. So let's go through the plots quickly. So first we have plots of the data we get from TVB. And yeah, so here we get all 4 regions activities. In blue, it's the excitatory population. In orange is the inhibitory population. The first 2 regions were modeled in nest. And as we have all neurons being identical and receiving identical connections, they are actually fired all at the same time. That's why the average activity looks like spikes here. If we had some randomness, which is possible, both in nest and in TVB-multiscale, we can induce some randomness in connections or parameters, and in that case, there would be a broader peak here. Also check that the activity has been scaled between 0 and 1, similarly to the activity of the actual TVB mean field model, although this is computed from instantaneous rate. So there has been some transformation of rates and hertz into activities between 0 and 1. And obviously, there's always some arbitrariness there. So these are the 2 spiking regions, and these are the 2 mean field regions. Obviously, the activity here is very different. Yeah, the same activity also shown here, only for the spiking regions. I will not go into these plots because they are the same. And then we turn into plots and analysis of the spiking activity. Here we have a computation of the mean firing rates by region and population. So they're all firing around the same firing rate we had for the TVB, around 20 Hertz. This is because of the input from TVB. If I had more time, I wanted to simulate first TVB only, in which case you would see, no, sorry, I would simulate Nest separately and TVB separately, and then you would see that TVB simulates on frequencies around 20 Hertz, while the Nest-only model would simulate around 10 or 15 Hertz, if I remember well. And it's only after we couple the two that the Nest network is driven by TVB and the firing rate increases to this number, due to the extra input from TVB, in other words. Unfortunately, we don't have now the time to do that. But I invite you to play with it. There was this input on the first cell, TVB, TVB Nest, or Nest only, and then you can run this notebook either with only TVB or only Nest simulation, or as we're doing now with both of them. And yeah, you see here spike rasters, the mean firing rate, and also there is a plot of synchronization between the populations of its region. Again, there is a mean spike rate. Then there are some measures of synchronization within its population, and obviously, as they're firing at the same time, this synchronization is very high. As I said, PySpike, another toolbox, is used for all these computations, but again, there is a wrapper around PySpike in order to be able to compute all this and easily plot them. But yeah, I will not go into more details. Only I'm going to show you a last plot here. Thanks to the multimeter device we defined, we can have also plots of the membrane potential, of the average membrane potential of the neurons of its population and region. And you can see here clearly the oscillation. Right, I'm not going to show any more plots. In the remaining time, let's try to play a little bit more, or I can show you what you could play with on your own. The most interesting thing would be obviously, to first, let's go up. It's very slow. I would suggest, first of all, as I said, to run first TVB only, Nest only, and observe the outputs, and then go back to TVB Nest. And then we can modify these inputs here. For instance, let's see what happens if we generate the spikes outside. Well, actually, you're not going to see much difference in that case at this level of description. But in this case now, we're going to generate the spikes in the transformer using the software Elephant, and we're going to send spikes directly to Nest instead of using devices that generate spikes in Nest. We can run everything again. And while it runs, so this simulation now is going to be a little bit slower because generating the spikes in serial manner to simulating takes a little bit more time, actually. But as we said, in principle, all these processes could run in parallel, in which case we would save time, actually, in some cases, when we generate the spikes outside Nest. What I'm going to show you is by changing the model to spikes, several other things change as well. And this is what I want to get to while it runs. So, right, so the model changes here and here, and this means that we also need to change some of the scalings. So we are actually under this case. So we don't need now anymore to scale the activity by the number of neurons. Instead, we define the number of neurons, which means we define how many independent spike trains we want to create, as I said, outside Nest. So here the scaling is different, first of all. And also, we decide how many neurons, how many independent spike trains we want to create with this average firing rate we get from TVB. And then these independent spike trains are transferred to NEST and then to the eventual targets, region, and populations in NEST using a spike generator device in NEST. That device only takes spike times and sends them to its targets. Nothing else changes. The simulation runs. You can see here now that it's a different transformer, a transformer, not just the linear one we had before, but a transformer converting rates to spikes. And a different device. Here there is a NEST spike generator device instead of a NEST homogeneous Poisson generator. Yeah, everything else is pretty much the same, but it took much more time, actually a whole minute to simulate. And yeah, not much else changes. And the firing rate also is going to be a little bit different. Well, I have tuned it to be almost the same actually. But for that, as you see, the original weight we used for the interface, which was this input here. So for the firing rate interface, we had this weight we defined above to be 5,000 times the number of neurons. Here we have 100 times that, and we define the number of neurons. Don't ask me why. I also need to look into more details to see why there is this difference in scalings. And another thing we can change is actually, or you can change later on, is you can, let's do the following now. Let's create a current interface, first of all. And let's this time allow coupling to be taken care in NEST, in which case we create one proxy node, a DC generating, current DC generating device in NEST for every sending population of TVB, sorry, region. And in that case, again, different scalings change so that we have pretty much the same result. Let me start it first of all, as we have only a few minutes now to start kernel. Yes. So we have changed now the model to be current, and also we have changed for coupling to be computing in the spiking network. This means that when I was configuring this model for you, I had to also play a little bit by trial and error and retune the scaling of the interface. So first of all, as coupling is computed now in TVB, it means that as coupling is computing now in NEST, the proxy nodes are actually the sending TVB nodes. And second, this coupling has to actually be reduced for the same result, more or less. Everything else is pretty much the same, but now when the interface is created here, you see that the proxy indices now are the TVB nodes, the third and fourth node, whereas the spiking proxy indices are 0 and 1. So really now we create a proxy for every sending TVB, and coupling with delays and weights is taken care automatically. We didn't need to do anything about this by NEST. Everything else is pretty much the same. Simulation is very fast, actually. The current is a very fast interface because the current generators in NEST are very fast. And we get pretty much the same kind of activity with a firing rate of, again, close to 24 Hz. check. Yes, well, there is also now a difference between excitatory and inhibitory population. Again, don't ask me why. I didn't have time to see the details of this. I just tuned them to be on a similar level of activity. So that was pretty much. There are other examples, more complicated ones. Let me see. So first of all, I think on this version I haven't tested, but the Netbind and Anarchy examples in principle should also run. Otherwise, there is also another notebook that uses Janssen-Ritt, another complicated, more complicated TVB model, and makes an interface to spiking network. And there is also this reduced von Wang notebook, which follows the model I showed you in the slides. Let me check only if you will be able to use it. Because it might be using a nest model that it's not available. But anyway, I also see that you manage to use it as well, so that's fine. I guess we have a few minutes for questions at this point, if there are any. Otherwise, I would say goodbye to everybody. I hope you got something out of this course, although it was, I guess, quite heavy and complicated. I only want to, yeah, so you see this is the example I showed you in the slides. You need to see the model that is using to make sure you can run it. Right, I'm afraid you cannot run this model currently, but well, as I said, we are under full development, so I hope that you soon can run this example as well. So there is a question in the chat. Right. All right, so if I understand the question, right, there is no constraint to sending activity of only one variable of the mean field model to the nest network. It's just that in most cases, in the examples I showed you, in all cases, we had one excitatory and one inhibitory population in every brain region, and it is common that only the excitatory population couples to other brain regions. This is the only reason we had actually only one state variable of TVB from every brain region, creating an interface with nest. Otherwise, it could be that we have actually we can have whatever we want. We can have many state variables. We can have different interfaces for the different state variables. Like one state variable might be converted to a rate and spikes, and another one to a current. Or we can have different interfaces for different brain regions. Everything is possible through this tool and quite easily configurable. So there is just not only one variable. It's just that one variable expresses the dynamics of one population at a specific brain region. Then another variable is the activity of another population in the same region or in another region. And then all of them relate through the equations, the mean field equations of TVB, and eventually each one of them can form its own interface with a nest network. It was just a coincidence of the example that only one state variable was communicated to the spiking network. I hope I understood well the question, and okay. So if there is nothing else, I would say goodbye to everybody, and I'm available for questions. I'm not exactly sure how. I could actually, I was gonna type now my email.